Welcome to Monday Night Calculus. My name is Curtis Brown, and I'm joined once again by Steve Kokoska and Tom Dick. I have really great news tonight. We are talking about local linearity, getting up close and thinking about that. Aren't we talking about local linearity? Steve's shaking his head. I thought
I'm
that was
talking
his.
about differentiation. Maybe you are, but I'm talking about differentiation tonight.
Well, then we're just gonna differentiate and roll with it. Um, anyway, so we're super excited though to have a good group of content for you guys tonight posted out there. If you guys have not yet had a chance, go down and look in the description. That student document is down there. And you can download that PDF and follow along with Steve and Tom. Tom's got some great technology tips for us, and we'll roll from here. I'm also going to put a little bit of information about the calculus textbook that Steve's got in his background there. So if you guys have a little bit of information or want a little bit of information, you can snag that from the chat as well. All right,
Thank
Steve,
you,
take it
Curtis.
away.
It is wonderful to be with you and Tom again. And judging from your misstatement about the topic for this evening, I'm going to guess you didn't do your homework for tonight. But
You know what? I did not.
oh man, I'll tell you. Hey, before we get started, one thank you to Mark Corrali, who has been advertising us on Facebook continuously. So thanks very much for that, Mark. We have some good problems tonight, some very interesting ones. I hope we get to the very last one. Tom posed a last minute question that I think is a great one, and we'll leave a little bit of that to you. But the first one is a kind of a long one. I'm going to do a lot with this with technology, sort of in the background. You're not going to really see a lot of my technology, but I'm going to do a lot with four functions here as I think about differentiation. And this seems kind of weird maybe when you read this problem. It says for each of these functions, we're going to compute values of that new function, f of 3 plus h, minus f of 3, all of that divided by h, for those, well, I guess 10 values of h. Well, I just want to remind you here, if we think about the derivative, the definition of the derivative, this is probably the definition that you teach your students early on, before they learn any rules for differentiation. It's this limit as h goes to 0 of x plus h minus f of x divided by h. And in fact, many of us actually teach this one first before we actually get to this general derivative, the derivative as a function. We talk about the derivative at a particular x value, and we think of this limit as h goes to 0 of f of 3 plus h minus f of 3 divided by h. If that limit exists, that would be the derivative of the function at 3. So, in fact, what I'm doing here, if I just think about this a little bit, is I'm looking at values of this expression for h close to 0. I'm going to look at values numerically and see if they appear to be zeroing in on any one single number. Now, I did a lot of these calculations with Mathematica. Tom's going to show you some with the TI-84. But I did a lot with Mathematica so that, well, I could present these tables to you kind of nicely. And what I did is I took a look at this function, this first function, which was a cubic polynomial. And in Mathematica, I defined a new function, g, over here. And then I created my table of values. For all those values of h, I found that value, g of h, where g of h is this expression. So let's take a look at this first table. As h gets closer and closer to 0 from the right-hand side, over here in this column, as it gets closer and closer to 0 from the right, the value of that expression seems to be getting closer and closer to 4. And in fact, as h approaches 0 from the left-hand side, smaller and smaller, closer and closer to 0, gee, but it also seems to be getting closer and closer to 4. That suggests that perhaps this derivative is equal to 4. Down towards the bottom, we have another function, a trigonometric function, the sine of 2x minus 6. Jeepers, there's no pi's in there. I'm a little worried about this one. But I did the same thing numerically in Mathematica. I defined this function g, and I created this table of values. And some good things seem to be happening here also. As h approaches 0 from the right-hand side over here in the left half of the table, that sounds kind of weird, sorry about that, the values of g of h seem to be approaching 2. I don't think that's exactly 2, but to 6 decimal places it's 2. And as h approaches 0 from the left-hand side, the value of that expression, g of h, is also approaching 2. Again, good numerical evidence that that derivative exists. There's more. This one's interesting up at the top. It involves an absolute value, the absolute value of 3 minus x plus 2 outside the absolute value. I did the same thing, and this is really weird. I had to check this a couple of times to make sure I was doing everything correctly. But every time I did this, as I approached 0 from the right-hand side, the value over here of that expression g of h is plain old 1. And as I approach 0 from the left-hand side, the value of g of h was negative 1. Well, that seems kind of weird. I'm not sure exactly why that's happening yet. But that suggests that the derivative does not exist because those values don't seem to be approaching a single value. And finally, down at the bottom here, our fourth function, the square root of x minus 2, same thing, same sort of table. So over here, as h gets closer and closer to 0 from the right-hand side, it sure looks like that expression is getting closer and closer to 0.5. And on the right-hand part of this table, as h gets closer and closer to 0 from the left, yeah, it sure looks like g of h is getting closer and closer to 0.5 also. I feel good about that one. I feel like that derivative probably, or that limit probably exists, and is probably equal to 0.5. Cool. So we're going to take a look at these from a couple of different angles here. And the next possibility is, the next one is, let's look at these graphically. So what we're asked to do is to take a look at each one of these functions, and we're asked to zoom in and estimate the slope of the graph at that point 3 f of 3. Now this is really cool, and thank you, Tom, for showing me how to do this. This is really cool on the TI-Nspire. Let me show you what I did. It's kind of hard to see on the right-hand side, but this is really cool. So on the left-hand side, just for my own benefit, I drew sort of a rough graph of that function f with all of the important points in there, all of the important features in there, but especially containing the point 3 f of 3, which is right there. Well, I wanted to get a really good estimate of the slope of the graph of f at that point. So here's what I did. On the right-hand side, I zoomed in quite a bit. And I don't know if you can see them all here, but let's see. I think you can see that my x range is between 2.95 and 3.05. The y range is between 2.05 and I think it's 1.95 down in the left-hand corner, kind of hidden. So I've zoomed in very close to 3f of 3. Now, we all know about local linearity, and we expect that if the derivative exists, this graph should look like a straight line, and it does. But in order to estimate the slope, what I did was the following. I can use a couple of features on the TI-Nspire to actually find this point on the graph of f, this point on the graph of f. Notice one is just a little bit bigger than 3, one's a little less than 3. And then I can use the Nspire to actually find the slope of the line connecting those 2 points. That's a really good estimate of the slope of the graph of f at 3. And notice that I got a 4 with a little bit of stuff in what? The 4th decimal, 5th decimal place? I'm feeling pretty good about what I did numerically. So I did the same thing here with f of x equal to sine of 2x minus 6. Let me see if I can find this here. Son of a gun, it looks like it's right on the x-axis. So I zoomed in quite a bit. went a little bit to the left of 3, a little bit to the right of 3, found the 2 points on the graph, found the slope, or connected those 2 points with a line, and found the slope of the line connecting those 2 points. I got a 1.999, pretty close to 2, what we found numerically, which was pretty cool. Once again, notice that the graph, as I zoom in on the right-hand side, the graph of that function f looks linear. Cool. Let's look at the next one. Well, I got kind of stuck on the next one. The graph on the left-hand side, be careful. They look kind of the same, the one on the left and the right. But the one on the left here is from -1 to 7 along the x-axis and from -1 to 7 along the y-axis. And notice there's a sharp edge or a corner there. And no matter how much I zoom in, I can't get rid of that sharp edge or corner. I cannot make that graph look locally linear. I cannot make it look like a straight line. And so just for the heck of it here, I'm going to draw a little bit. If I were to take a point just to the left of 3 and just to the right of 3 and find the slope of the line connecting those 2 points, well, the slope would be pretty darn close to 0. But I don't think that has a tangent line that's equal to 0. That the graph of f does not have a tangent line at that point 3, f of 3. I cannot make it flatten out. I cannot make it look locally linear. It certainly seems to me that the derivative does not exist at 3, and I think that was backed up by our numerical table. Finally, let's take a look at this last one, the square root of x minus 2. Here's what it looks like on the left-hand side, and let's see if I've got 3. Yeah, there's 3. There's the point 3, f of 3. I zoomed in around there. And once again, I went a little bit to the left of 3, a little bit to the right of 3. Found 2 points on the graph, found the line connecting those 2 points, found the slope of that line. It's pretty darn close to 0.5, very close to what we did numerically. That's nice. That's really cool. Nice problem to show graphically, to show numerically. Now let's take a look at this analytically. Now, I didn't write a lot of this down in the actual document, Curtis, but I did write a little bit off to the right-hand side here. So based on the numerical and the graphical evidence, let's see if we can find the derivative of f at x equal to 3. So what I did is I actually, on the right-hand side here, is I actually took the analytical, the symbolic derivative, and evaluated it at 3. So the first function is a polynomial. I take the derivative term by term. I think I got 3x squared minus 8x plus 1. I evaluate that at 3. I got a 4, and that is confirmed by our graph. That's confirmed by our numerical tables. I feel really good about this one. I believe that the derivative of f at 3 is 4. For part B, interesting, again, no pi's in here, but this worked out kind of nice. The derivative of f is the cosine of 2x minus 6 times the derivative of the inner function, chain rule working here, which is 2. Take the derivative at 3. 2 times the cosine of 0, 2 times 1 are 2. Yep, I feel really good about this one. That confirms what I found numerically. That confirms what I found graphically. In C, well, I didn't write anything analytically, and Curtis, maybe we can put a question off in the chat here. I wonder how I would go about finding the derivative of that function in C analytically. There is a way to do this. Kind of long, but there is a way to do it. But I'm convinced by the numerical table. I'm convinced by the graph. I'm convinced by zooming in that I cannot make that graph flatten out or straighten out, that the derivative does not exist. And finally, in part D, there's the derivative of that function f. Let's see. I guess maybe I should have rewritten that to start this out. So that function f, I'm going to write as x minus 2 raised to the 1/2. The derivative of that is 1/2 times x minus 2 to the minus 1/2. Okay, derivative of the inner function is 1. I'm going to rewrite that a little bit as 1 divided by 2 times the square root of x minus 1. And I'm going to take the derivative symbolically here. I'm going to plug
Hey,
in.
Steve,
Yes.
suggestion on part C.
Go. Good. What is it?
Rewrite it as a piecewise defined function.
Okay. And then do
That
what?
was one step
Okay.
to kind of get us off the ground.
That is a start. I like that. It's a good start. Down in D, I'm going to evaluate the derivative. I plugged in a 3. I got 2 times the square root of 1, so that's 1 divided by 2, so that's a 0.5. I feel really good about this one. I think the derivative of that function f at 3 is 0.5. So wow, we've been able to take a look at derivatives here numerically, graphically, symbolically. We've seen an example of a function where the derivative does not exist. And by the way, common sort of question on the AP exam where there might be a sharp corner or an edge, and students would have to identify that and know that the derivative does not exist there. Often a reasonable answer is that derivative does not exist because there is a sharp corner or edge. And Tom, time for a little technology?
Sure, Steve.
Okay,
All right.
there you go.
Okay. All right. I'm hopefully getting my online TI-4 up and running and in view. I hope you can see that.
Yes, looks good.
Great. Okay. So this will just be, I guess, a kind of dynamic version of what Steve was doing on the 84. So you can actually, we'll do some of the calculations live and some of the zooming in live. So I'm going to go to my y equals menu. And you can see here, I've already got those 4 functions are entered in as y1 through y4. So I took the liberty of going ahead and putting those in. In terms of numerical calculations, I really like to do this kind of from scratch on the calculator page to start with. Steve made a nice table, but for example, that y1, which was the cubic, is let's actually just build a difference quotient and evaluate it. So I'm going to pull up a fraction template here and get my y1 and evaluate that at 3 plus, well, let's try 0.001. Okay. Then minus y1 of 3. And then we'll divide by that 0.001. And there we get that value there at 4, which is very close to what we're looking for. Let me do another one, but now let's take advantage of the fact that I've done all that typing once. Let me just go up there and echo it down. I'm just going to make the plus 0.01. Let me go over and change that plus to a minus. I want to be careful here. Let's see. I'm going to need a minus down here too, I believe.
Mm-hmm.
And so let me minus in there. There we go. Great. So we've got those 2 values. And I'm going to try something just for the fun of it here. I'm going to try to calculate the derivative of this using the built-in derivative on the 84. So let's go to the math menu. And down there at number 8 is the numerical derivative. Okay, let's enter that. So we're taking the derivative with respect to x of y1. And we're trying to take that derivative at 3. Now this is numerical derivative. So what the numerical derivative is doing is a difference quotient, much like what we've just done by hand here. I say it by hand because we've done the hand entering. We did let the calculator do the calculation. Wow, that ended up being exactly 4. And wanted to point out that what the numerical derivative is actually an average of a right-hand difference quotient and a left-hand difference quotient. And when I say right-hand and left-hand, I would refer to this first one up at the top, where it's 3 plus 0.001, where we took a point just to the right.
Mm-hmm. Yep.
That was a point just to the left. So there's a left-hand difference quotient, right-hand difference quotient. We could say we're looking at the limit of the difference quotients from both sides. They both have to approach the same number for the limit to exist. And that would be the derivative exist. And what the numerical derivative is doing is actually averaging these. In fact, what would happen if we averaged these two numbers right here? Let's enter that one. I'll actually put a parenthesis in front of it. And then we'll add the second number. And divide by 2.
How about
Very,
that?
very, very close. Yeah. So, and so that's really what that numerical derivative is doing. Now, the counterpart to that, in terms of graphics, is if we were going to, let me go back to my y equals menu. There's that y equals the cubic. If I go to a graph, I'll tell you what, let's start out with a zoom decimal window, see if that works. Oh, that's right. I guess I had all 4 functions in there. I might go back and just make it a little less busy by turning off all the ones but the first one. That startled me a bit. There we go. All right. So here's the graph of the cubic. The window, let's see, the point of interest here is at x equals 3. We might want to do a zoom fit. Oh, wow. So let's see. Tell you what interest is, let's go to that 0.3.
Yeah, I think I went, if it helps, Tom, I think I went -1 to 7 in both directions.
-1 to 7?
In both directions. I think will give you everything you need.
On the window? Okay.
Yes, sir. I think
All
so.
right. Okay, so
Give that a shot.
all right. So -1.
I mean, you won't be able to trace nicely, but it gives you all the features.
Okay. Let's graph that. Or I could
Got to do that on the y-axis also.
yeah, I could do the actually let me try this. Let's try a zoom square. Oh, that's interesting.
So that changed your window then, huh?
It did. Okay, yeah, let me try that again. So I'll do -1.
Looks like, Tom, you might have a -8 instead of a +8 in your equation. Is that true?
Oh, let's see. Did I miss?
Yeah, I think that's a
Copy
+8.
I think you're right. All right. It's interesting that didn't affect our derivative, isn't it? Ah, there's a concept there.
But
Yeah,
another-
yeah, there you go.
Oh, this had to say it didn't matter what that constant was on the end. We got a 4. Okay. Now let's try that graph again. Let me try it. Does this one show? Ah, this is much better. Okay, now we're on the screen. Okay, thank you for catching that error, typing error of mine. Okay. So this is a zoom decimal window. And if I trace over to that point of interest, let's see, it was at x equal 3. Okay, so let's go over there. So 3 comma 2 is our function. And I want to zoom in on that point. So let's go to the zoom and zoom in. And I'm going to do another zoom by just hitting enter again. And well, this was surprising. I have a suspicion here. Let me go to my zoom memory. And
Yeah,
I'm wondering if my factors might be kind of weird. Ah, there we go. All right, let's change those both to 4. All right. We'll try
There
that
is another
again.
question I have
Okay.
in the chat, but I'm going to hold it for just a second.
So we'll trace it back to that. 3 again. And this time we'll zoom in with equal scale factors. And that's very important. So when we're checking out this kind of local linearity view of differentiability, we want to zoom in with equal scale factors. And that's what had happened to me is I had unequal scale factors because I think the last time I did this, we were looking at limits. And sometimes you just do kind of a horizontal zooming in. Okay. So I've zoomed in just about 3 times here, and it's already looking quite linear. Okay. It's not exactly linear, but it's getting closer and closer to a straight line. And much like what Steve did, what we could do is turn on our trace and just trace a couple of pixels over. There we go. We're at 3.003125 and 2.0125489. Okay. If I quit off the graph screen and type in alpha y, that's that trace value has been recorded to the screen now. Okay. And similarly, we could put in the x, and that's the x value that corresponded to that. Then if we return to the graph, turn on our trace, let's go a little bit to the left of our 0.3. So I've gone just a couple of pixels over. If I go back to my calculator screen and pull up y, there's that y value. And if I put in x, there's that x value. Now I can kind of keep track of these. That first y value that you see on there was 1. Well, we could just take those 2 x values and take the difference and divide by the difference in the x values. This is exactly what we do when we're doing the slope of a line. Let's see what happens if we do that. So I'll get a parenthesis. I'm just going to arrow up and grab that first x value, subtract, arrow up to the second x value, and then divide by the difference in the x values. So I'll arrow up, get that first x value, subtract that second x value. Boom, looks very good. So again, so graphically, we're seeing that local linearity effect. And that's what, so Curtis really wasn't wrong when he was saying some of this is about local linearity. So, but
I mean,
this is
come on, man. Just because I was stealing a little bit of your thunder.
So, and this is the one other thing I would show, but maybe let me take a pause there for just a second to see if this is a good time to field the question that Curtis got off of the chat.
Yeah, so there was another question here, and I've been trying to think about it myself. So would the average of the left and right numerical derivatives always give the same result as a symmetric difference quotient?
Oh, okay. Yeah, it's something you could just it's actually just kind of a little bit of an algebra exercise. It's actually write down those two. and it would be exactly the same as the symmetric.
Yeah.
That's a
Which
wonderful.
I thought was kind of a cool little suggestion.
It is.
So thank you, Gerald, for that.
Excellent. Yeah. And in fact, it's the symmetric difference quotient is in some sense what I just done here by hand.
Right.
By pixeling over a couple of pixels to the left and to the right and taking that difference quotient, I did a symmetric difference quotient. And it's really quite close.
Tom, I don't know if you're going to do this or not, but would you go to the window for me one more time?
Okay. The actual window settings?
Yes, please.
Oh, okay.
I'm going to ask you to do a couple things here. Try a couple
right.
things. Change those back. Change X min and X max to -1 and 7.
Okay.
And change Y min and Y max to -1 and 7 also. Beautiful. Let's just take a quick look at this graph. Okay, so we've got almost all of the important features on there. Maybe we could go a little bit higher on the y-axis. Maybe we could make that even a -2 there. Let's make that a 10. And let's make X min like -3 or something. Beautiful. Okay, I feel much better about that. Okay, so what we've done is we've just figured out, and we've used this formula we learned about in problem number 1. We've estimated the derivative of this function at 3. So now let's go to the y equal menu. And let's go down to y5. And let's start a new function, left parentheses, y1 of x plus, x plus 0.001, close parentheses, minus y1 of x close the right parentheses, divided by 0.001. Now, what we've learned, I think, theoretically, is that that expression for any value of x is an estimate of the derivative. It's not a symmetric difference or anything, but it's an estimate because h is pretty small, 0.001. It's an estimate. So what is this doing? It's a function which gives you an estimate of the derivative of this function, y1, at every value of x. So I think this is a great way to explore the derivative of some functions that we have no idea what the derivatives look like. For example, the sine, for example, the cosine, for example, the tangent. Now, this one probably won't be too amazing, but now hit the graph key. And we can talk about the relationship between those two graphs, where the blue graph, the original one, is increasing. What do you see about that second graph? And by the way, that's a pretty darn good estimate of the derivative of that function, isn't it? Yeah. Even for 0.001. And if we wanted to, Curtis, as someone mentioned, if we wanted to, we could even get a better numerical estimate by just taking a smaller value of h or taking a symmetric difference with a small value of h. We could even get a better numerical approximation. I think that's just really cool. That is a great visualization to get students thinking about, well, what does the derivative really look like? And what does it tell you about the original function? Now, I don't know, I don't want you to do this, Tom, but you can just tell me, is it possible to go one more step if you wanted to? Could you take the derivative of that y5 in the same way numerically?
Yeah, I think so. Yeah.
Think you could? Okay. Interesting.
In fact, what I thought I would do is go back to the y equals. I'm going to turn off y1. And one of these that was kind of interesting was y3.
Yes.
An absolute value in it. And I'm going to edit Y5. I'm going to make those
Okay.
Y1s
Yeah,
actually
cool.
Y3s.
Yep.
Okay, so
Yep.
and I know Curtis hates that I'm doing this.
Drives me crazy every time I see you do that bar and Y bar stuff. What are you doing?
All right. And I'm going to try a zoom decimal window here. This is going to graph both the Y3
Yes.
and this difference quotient for Y3, which should be an approximation of the derivative.
Correct.
So let me try a zoom decimal window here. Oh,
That is cool, isn't it?
yeah. And, you know, I think you made mention of this, Steve, that that sharp corner graph of the absolute value, the function involving absolute value, to the left of 3, it looks like a perfectly straight line, which it
Yep.
is. And that straight line has a slope of, there it is, -1.
-1. Yep.
And to the right of 3, it looks like a straight line of slope 1. And sure enough, the derivative is 1 to the right of 3. But that means right at 3, we have a mismatch of left-hand and right-hand limits for our difference quotients. So the limit doesn't exist, and the function's not differentiable at that one point. It's differentiable every place else, but at 3, the derivative fails to exist. And that sharp corner is our graphical evidence. And as you said, if we traced on the absolute value over to 3, so we're right on that sharp corner. If we were to zoom in, it doesn't matter how many times we zoom in, it's never going to straighten out. It's because it's not differentiable. It won't have that property of local. It's funny, I keep hitting enter, I'm zooming in and in, but really, to appreciate that the picture has changed, I would need to trace so you can see how close we are. See how the increment there is tiny. So we are really zoomed in a lot, but that sharp corner is just as sharp as ever, and it will never straighten it out. So it's definitely not differentiable. As soon as we get away from 3, everything's fine. In fact, this function is piecewise linear. And I know that was a suggestion that came. If we did it as piecewise function, that would be a way to analyze the left and right hand limits and see that the limit doesn't exist. Okay. All right. I think I should turn it back over to you, unless you or Curtis, is there anything we should continue to look at here? Or?
I'm good. That was great, Tom.
Right.
I mean, the only other thing possibly, you don't have to do this, is, I mean, you can create the kind of tables that we showed. You could create those perhaps even in the stat list editor, or even on in the table feature, which I prefer, but I know you like the stat list editor. But in the table feature, if you were to define a function like I call G, you could certainly create those table of values pretty easily there.
Yeah, the one kind of warning I would give to teachers about that is if you do use the table feature, you're going to end up using X as that H value.
Yes.
And so there is, I think, some potential there for a little bit of confusion, but as long as you can keep straight that you're using the variable for the increment rather than the specific point, you're okay. And then that's why I tended to do it right on the calculator page, you know, onesies is so I can really keep a focus at X equals 3 and the H value was this small 0.001, whatever. So,
yep.
All right. Okay, I'll stop the share and turn that back over to you.
All righty. Let's see. There we go. Let's try this. Okay. So I don't know why this says number 4, but it's really number 2. I don't know what happened there.
Well, 1, 2, and 3.
Oh, no, I know what it was. So 1 was the numerical. Okay, so here we go. Okay. All right, so we have a drone now rising vertically over the time interval 0 to 10. And the table shows values of the upward velocity. So this drone is going straight up. This is a TI drone, by the way, Curtis. And the velocity v of t is measured in feet per second at selected values of t. So there's our table. And we've only got two questions here. What's the average rate of change of the velocity over the time interval 0 to 10 seconds and indicate the units of measure? Well, look, we need to know how to compute this average rate of change. This is a very common question on the AP exam, very common on the free response portion to get students into a problem. It's just v of 10 minus v of 0, all of that divided by 10 minus 0. Yep, I think they need to know that formula. How do I find that? Well, I go to the table here. V of 10 is 32 minus 2. That's v of 0 over 10 minus 0, 10. 30, I did a little bit of simplification. I think that's just 3. And I think the units of measurement here are feet per second squared. On the exam, look, some of the scoring guidelines have changed a little bit. And as you know, all of the points now are accounted for, and they're really trying to assess what students know conceptually. But I would like to suggest that when you do a problem like this, it's not hard to write these steps in here. I mean, we know that our students are good enough to know this formula, to look at this table and almost automatically say, oh yeah, it's 30 over, it's 3, and just write down the answer. But don't forget to show your mathematical setup. Don't forget to show the calculations that lead to your answer. In part B, using the data in the table, let's estimate the instantaneous rate of change of the velocity at time t equal 4. Well, this is a little different, and it's kind of a throwback question to the AP exam from many years ago. It doesn't tell you what values of t to use. And so sort of intuitively, sort of common sense here, I think I'd want to find values of t that are close to 4. And so I'd want to use 3 and 5. So I'm going to find the average rate of change. It's v of 5 minus v of 3 divided by 5 minus 3. I go to the table for those values, and I got an estimate of 2 feet per second squared. Now, I think that's quote unquote the right answer, but there are other ways to answer this question. I mean, I could use other values in this table, other values of t, to estimate the velocity at time t equal to 4. Who's to say that using t equal 3 and t equal 9 isn't such a bad idea? We don't know exactly what the characteristics, what the behavior of this function v is like. And so it could be that 2 other selections of t might give you a better estimate. So that's why on the exam, I think you will always see something like, using the data in the table, estimate the instantaneous rate of change of velocity using t equal 3 and t equal 5 at t equal 4 seconds, and indicate your units of measure. There'll be something in there to indicate to you what
Hey,
the interval
Steve,
that you should use. Curtis.
should your third denominator there be a 2?
It is a 2, Curtis. It's very difficult to see, but it is a 2.
Okay.
Thank you.
Was just checking.
Thank you. Boy, you're on the ball tonight, Curtis. Thank you.
No, I'm not. The participants are, though.
Very good. Thank you very much for catching that. Cool. Okay, let's take a look at another one, Tom. Is that all right?
Sure.
Okay.
I would make this one comment, Steve, and
Yes.
sorry, I know early in my teaching of calculus many years ago,
Yes.
a question like that one would have stumped my students.
No kidding. Why?
And well, it was because we never worked with tables.
Sure.
It was we worked with difference quotients only long
Yes.
enough to do the definition of derivative.
Yes.
They were all for let's get to the shortcuts, let's get to the rules like bringing down the exponent and subtracting 1 for
Yes.
hours. And so something like that, they would say, well, this is not a fair question because you haven't given me a function that I can take the derivative of. And I really love these questions because it really brings us back home to what is the meaning of the derivative. It is a limit of difference quotients. And you can always approximate it by using a difference quotient, or in this case, we're doing an average velocity to approximate an instantaneous velocity. So sorry, just jumping on the soapbox, but I think these are fantastic questions, and they are really quite common to show up on the AP exams.
Yep. All right, number 5 is kind of a neat question, and especially part C. I don't want to call that a proof, but it's got a lot of symbols in it. I won't go through that in gory detail, but it's kind of a neat result. So here we have a function f defined as 2x squared minus 3x plus 5. Note that it's a quadratic. And what we want to do here, in keeping with a lot of the things that we've done this evening, is we want to find the slope of the secant line through those 2 points, 3f of 3 and 7f of 7. So I skipped a little bit here. I found the 2 points on that curve. I plugged in a 3, I plugged in a 7. I hope I got that right. So the points on the curve are 314 and 782. And so the slope of the secant line is the difference in y's divided by the difference in the x's, and I got a 17. Now, I didn't ask here for the equation of that secant line, but we can easily get that if we wanted to. That's not the point of this problem. In part B, we want to find the slope of the tangent line to the graph of f at the point 5, f of 5. I just want to think about this for a second. Is there any relationship between that point 5, f of 5, and the other two up there in part A? Well, you'll notice that the x value 5 is right smack dab in the middle of 3 and 7. It's the average of those two values, 3 and 7. So I'm going to find this derivative not by doing anything numerical or graphical. I'm going to do this symbolically. I'm going to find the derivative symbolically. I got a 4x minus 3. I'm going to plug in a 5, and if I've done everything correct here, I've got a 17 there also. That's curious. So that the slope of the secant line between those 2 points is 17. The slope of the tangent line is exactly the same. So that sort of suggests this question. And Curtis, I apologize, there are a lot of symbols floating around here, but our students should still be able to do something like this. Let's suppose we have this function g, which is an arbitrary quadratic, where a, b, and c are constants, ax squared plus bx plus c. I want to show that the slope of the secant line through those 2 points, p and q, with x equal p and x equal q, is the same as the slope of the tangent line to the graph of g, where x is equal to the midpoint of p and q, or the average of those two values. Curious. So let's see. To find the slope of the secant line, here's what I did. I started out by looking at that difference quotient. I took q and I plugged it into that quadratic. I took p and plugged it into that quadratic. I did a little simplification. Let's see, the c's will cancel. And then I did a little bit of factoring here. Let's see, I think I coupled or grouped this term and this one and the remaining two, and I took out an a and I took out a b. And let's see, this expression was the difference of two squares, holy Toledo. And then I could factor out a q minus p out of both of those terms. And finally, one cancels. And after all of that, in symbols, I've got an a times the quantity q plus p plus b. So I want to show that that slope is the same as the derivative at p plus q divided by 2. There's the derivative of g. That's pretty straightforward. Let's see. I plug in a p plus q divided by 2. The 2's cancel. There's my a times p plus q plus b. Son of a gun, those two are the same. And that's a neat problem. So you might think that this only works at special points along this quadratic, but we've just shown if you take any points on that quadratic, any at all, and find the slope of the secant line and then the slope of the tangent line at the midpoint, they're going to be the same. That's really cool. Go ahead, Tom.
Yeah, another way to think about that is people are talking about the symmetric difference quotient. What this says is it doesn't matter how small or big your H value is. If you do a symmetric difference quotient on a quadratic, you'll always get the right answer exactly. So,
That's right. How about that? Isn't that something, huh? Yeah.
very neat.
Okay. All right, Curtis, we've got one more for participants to think about this evening, and we'll call it a night. This is a very interesting function. It is f of x is equal to the cosine of x to the 2/3. And what we'd like to know is, does f prime of 0 exist? So in order to figure that out, I think we've got to investigate this numerically, graphically, and analytically. And actually, I'm going to start by looking over on the right-hand side. Then I'll look at a couple of graphs, and then if you'd like to do anything with this graphically or on the 84, that's fine. Here's the way that I might attack this, sort of naively. First thing I'd do is I'd take the derivative of that analytically. So let's see if I've done this right. F prime of x is minus the sine times x to the 2/3 times the derivative of the inner function, which would be 2/3 x to the minus 1/3. And I did a little bit of simplification. I've got the minus 2 up there in the numerator, and I've got the 3x to the 1/3 down there in the denominator. Let me add a little bit. Now, if I wanted to evaluate f prime of 0, what happens if I plug in a 0? Well, I can't evaluate that function because I've got a 0 in the denominator. Well, I've also got a 0 in the numerator, but I've got a 0 in the denominator. And that sort of just says to me initially, well, the derivative doesn't exist. I'm done. But let's take a look at this graphically. This is a weird function. There's a graph between minus 10, x equal minus 10 and plus 10 up here on the top left. And I don't really see a sharp edge or a sharp corner. And I just have to remind myself that, 0 is in the domain of this function. So it is continuous at x equals 0. The cosine of 0 is equal to 1. So I did a little bit of zooming in, not much, but a little bit, expecting to see some other feature of this graph that might give this away, but I don't. It doesn't look like a sharp corner. It doesn't look like it's smoothing or leveling out yet. So I don't know what the answer to this is. Tom, would you like to do anything with the 84 to finish up?
Sure. Yeah,
Okay.
let's take a look at exactly this function. So,
Okay.
So here's my TI-84. I've got that function cosine of x to the 2/3. And let's kind of look at it graphically. I'll go ahead and do a zoom decimal window here. And it's hard to tell just looking at this scaling. Is that a sharp corner up there, or is it? Well, it's hard to tell. It looks like it's a little. I just don't know. But what I want to do is zoom in on it. So let me go ahead and hit trace, so I get up to 0, 1. So that's the point on the graph. It's certainly defined at x equals 0, but is it differentiable there? Well, let's try to zoom in. It's still.
I can't really tell, huh?
Fine-ish, but maybe not. Let's try zooming in again and again. And you know what? It's just starting to look pretty smooth.
Yeah, it is.
Looking flatter and flatter. Yeah, it looks all right. So, well, what's the calculator tell me? The numerical derivative. It's going to do a symmetric difference quotient. I mean, what's that look like? Let's go ahead and take a look. We'll do an n derivative with respect to x of y1. And that's at x equals 0 is the interesting place. It says the derivative is 0. Okay.
Hmm.
But it is a numerical derivative, so that's just an approximation. So if folks are wondering, looking at Steve's work there, clearly when you use the chain rule, you end up with an expression that's not defined at x equals 0. But this is the problem. I should give a shout out to a beloved late colleague, Steve Olson, is the person who showed me this example first. This is makes us read the chain rule really carefully. What the chain rule says is that chain rule expression, if it exists, will give you the right derivative. But if it doesn't exist, you've got to re-examine what's going on. And so if we actually do a limited difference quotients on this, we will get a limit of 0 for the limited difference quotients at x equals 0. So the derivative does indeed exist. It is equal to 0. But if we just kind of blindly use the chain rule and say, oh, that expression doesn't exist, therefore the derivative doesn't exist, that's not quite correct. So it's a subtle example, but kind of a cool one. And this is one where the graphical evidence is pretty compelling.
Sure is. Yeah. This is a great one for tomorrow morning at 8 a.m. in class.
It'll wake people up. So,
thanks, Tom.
There's lots of cases where when the chain rule expression doesn't exist, the derivative doesn't exist either. But this is an example where that's not true. So we've got to be a little bit careful. Okay. I'll turn it back over to you.
All right, Curtis.
Probably about out of time. Okay.
Yeah. Thank you.
I think that is it. Just about it for time. So yeah, it was a great session tonight, guys. A lot of good problems in there and good calculator stuff. So hey everyone, we are, I guess today is September 22nd. I genuinely have forgotten when the next day is. We are coming back. We're actually taking the month of October off for Monday Night Calculus. Our next date is on November 3rd, which is the Monday, and we'll be looking at IVT, EVT, MVT, those great calculus
EVT,
theorems that we can chat a little bit about. So be looking for that. I'll be posting the YouTube link here shortly. As always, you can certainly email me for the professional development content, Curtis at TI.com. And don't forget to send me a reminder, because tomorrow I'll probably need to post the solutions.
I'll send them to you.
Odds are I'll probably miss it in the first few hours of the day. So I definitely need a reminder. So please reach out and give me that, as well as asking for that development certificate. Hey, we will look to see you guys here at the TI Calculators YouTube channel here in about a month. Thanks very much.
Thanks, Curtis.
And we'll talk soon.
All right.
Thank you.
Bye-bye.
That was great, Tom.
Oh, it's good.
Yeah, I like that.
Hey, sorry I didn't